Welcome to section 1.7 on continuity. This section introduces the concept of continuity at a point and at all points in an interval. And I want you to recall that an interval, we used interval notation, so brackets, if I had something, an interval from A to B, that means it's in between A and B, and the brackets, actually I made a little bracket here, the brackets show that the endpoints are included. So that's what we use for interval notation. This will lead to the next section where we'll develop the concept of a limit. So we're going to be talking about limits after this. You should be able to identify whether well-known functions are continuous or not continuous. Recognize that continuity on an interval can be represented by a graph with no breaks, no holes, and no jumps. Okay? Introduction to continuity. A function is said to be continuous on the interval a comma b, including a and b, if it is continuous at each point in the interval. Loosely speaking, we say a function is continuous on an interval if it has no breaks, jumps, or holes in that interval. You may have heard the following definition of continuity. And now this in green is what I love. A continuous function has a graph which can be drawn without lifting the pencil from the paper. So that is basically what we're doing, is if you draw a graph where you lift your pencil, it's not continuous. Continuity is important because continuous functions have properties that are important in calculus and more advanced mathematics. Definition. Functions which are not continuous are called discontinuous. So you'll see this term we'll be using is a discontinuous function. Let's talk about some discontinuous functions that we looked at. Well, we've already done rational functions, and they usually will have an asymptote of some sort. So rational functions have some discontinuity to it. Not all, but a lot of them do. We had some piecewise functions that we've talked about. Piecewise functions had some holes or breaks in the graph. And the tangent function has holes and breaks into it, and so all the rest of them, because sine and cosine is continuous, you've got cotangent that can have discontinuity along with secant, and let me erase this line, cosecant. A discontinuity occurs when a function is undefined at an x value. So usually when we're looking at our interval, you're looking at x value interval. Okay? A function that contains a vertical asymptote is an interval that is not continuous because there's a hole in it. A function which is a piecewise defined for all values of x, but which has breaks or holes, is not continuous on intervals. Okay? So basically, and we usually don't say the word not continuous, but it's discontinuous. Here's an interesting web link on the basic definition of continuity. And so I have got things on my website that I'm going to have you do, but don't worry about this web link right yet. I'll show you this in class. The following are functions that are continuous on the entire real number line. So let's look at it. A polynomial function. So let's call this 1, 2, 3, 4. So let's do a little picture of each. All right. A polynomial function, which we talked about. So here's number 1. So I'm going to do a little sketch here. And polynomial functions had a lot of turns and whatever. And notice there's no breaks. I didn't pick up my pencil once. So that is continuous on the entire number line. Exponential functions. Exponential functions grow quickly. Exponential functions look like this. And if you see, it keeps going forever and ever. I never picked up my pencil. Positive integer power functions. So like if I did x squared or x to the fourth right here, a parabola. Notice I did not pick up my pencil for that either. And the sine and cosine function, which is basically the same function, just one is shifted. But if I did the sine function right here and kept going, I never pick up my pencil. And then the cosine function goes from here to here, I didn't pick up my pencil. So those functions are continuous on the whole interval. All right? Now let's practice how we do this. Now I've graphed some of these, so you can graph and look at them too, but I'm going to go in between my calculator and this. So we want to determine where this is not continuous or discontinuous, if you will. So the function I have there, I look at it and say, oh, it's in a fractional form. This is a rational function, which we talked about. And rational functions will give rise to vertical, horizontal asymptotes usually. And if we look at this one again, what we did was we want to try to find where there's holes in the graph. So remember when we learned about vertical asymptotes, we took the denominator and put that equal to 0 to see if they had any vertical asymptotes. So if I do x squared minus 4 equals 0, x minus 2 times x plus 2 equals 0, make my big T, I know that there's a vertical asymptote at x equals 2 and one at x equals negative 2. Okay, so if I were going to sketch this. So this is not continuous, or if you want to say this is discontinuous. And where is it discontinuous? Well, it's discontinuous where x is 2 and x is equal to negative 2. All right, so if we were to make a little sketch of this function, and I'm going to show you the actual graph in a minute, we know at negative 2 there's a vertical asymptote and a positive 2. So here's my vertical asymptotes. And we also learned that we can see if it has a horizontal asymptote, if the power is greater than the numerator power, then there isn't any. So there isn't any horizontal asymptotes, excuse me. And if we plug in 0 for x, we'll see that the point 0, 0 is on there. So this graph kind of looks, well, I'll actually show you what the graph looks like. So let's go back to my first one, and this is what the graph looks like. And I shouldn't say that. The power is greater in the bottom, so it's the horizontal asymptote is y equals 0. I misspoke myself, I'm sorry. So if you look at it, you can see it's discontinuous here. So I'm not, from here over, when I follow this down, that's continuous here, but then there's a break, and then it's continuous here, but then there's a break. So it's continuous in spots, but it's, as a whole, the whole function is discontinuous. Okay? So let's kind of go back to our notes a little bit. You can actually answer this two ways. This is a discontinuous function if I was going to look at the whole function, and so let's sketch this here. So we'll have a little sketch of this in our notes. Okay? So basically, you can write this a lot of ways, and we're going to talk about this in class, but if I'm looking at the whole function in its entirety, I would say it's discontinuous. But if I break it down into intervals, okay, so it's discontinuous if I look at the interval, and you can't use bracket here, from negative infinity, when x is from negative infinity to positive infinity, is discontinuous. But I could break this down and say, okay, is this function discontinuous, say, from negative infinity all the way up until, we'll say, negative 4. Well, if I were to come here to negative 4, I'm like, oh, this function keeps going forever up to negative 4. So here, it would be continuous here on this interval because there's no holes on that interval. But if I looked at the whole thing, there would be holes. So I just want you to see that it depends on the interval that you're given. Okay, let's look at this next one. All right, so I have g of x equals, it's another rational function. And again, we're going to look at the vertical asymptote to see if there is any. So I look at it and say, if there is one. So I take my denominator, put it equal to 0. And when I do that, I see x squared equals negative 1. So that'll never happen. So there are no vertical asymptotes. There are none. Okay? So I'm like, okay, that's great. And I want to see if it has any, so this is a vertical asymptote, if it has any horizontal asymptotes. So I look at the horizontal asymptote here, take the highest power in the numerator and denominator. Again, I memorize that. That's y equals 0. So I'm like, okay, I wonder what this looks like. So let's graph it. So I actually graph this one too. So let's go to the next one. And I graph this one, and if you look at it, there is no breaks in it. Okay, it has a y. It has the horizontal asymptote at y equals 0, but there is no vertical asymptote. It looks like I could draw this without picking up my pencil. All right, so let's do a little sketch of this for our notes. So this one, for the entire, kind of looks like that a little bit. So yes, this looks like it's continuous. This looks like it's continuous. It's a U everywhere. Okay, so that's continuous everywhere. Now the next function I'm going to show you, I hope you recognize, is this function continuous. This is a piecewise function. And we've done a lot with piecewise. And we want to see if there's any holes or breaks into it. So basically what I had you guys do when we did this was to see when we graph this. So here this piece is 2x plus 1. This piece is x squared minus 1. And the break is at 3. So let's see if it's the same y value. If it's the same y value at 3, there's no breaks. But let's look. So I'm going to do 3 here. If I put a 3 in here, I get 7. And I have to go lower. 2, 5, 1, 3, and so on and so forth. Okay? That is not on that graph. So you're going to go up to 3, 7. Here, 3 is actually on the graph. If I put that in there, I get the 0.38, and then I keep going. If I put a 4 in there, I get 4, 15, and I can keep going and going and going. And if you were to graph it, you'll see this is I have a line here, and this, and then there's a break because the 0.37 is here, and then it goes to the 0.38 for the next piece. Do you see where there's a break there? And this is a part of the parabola, which is x squared minus 1. So this is not continuous, it's discontinuous at 3. There's a hole there. So let's, when you were to do this, and you could actually graph this yourself, but it's a line. So here's 3, 7. Okay, so we'll pretend this is 3, 7. So this line, okay, basically kind of goes like this. And then it starts up here at 3, 8, and it starts to be a parabola. It just doesn't look like that because I have it zoomed in. But you'll notice there's a hole there at 3. There's a break at 3. So x equals 3. There's a break in the graph. So it is discontinuous. Okay, it's discontinuous. Now the question I have for you is, what would have made this continuous? Well, so if I were to do this and look at this where the hole is, okay, what would have made this continuous is if when this new graph started, if it was in that part right there, that would have been, even though it would have been piecewise, I could have not picked up my pencil and done that. So that, if we could have fixed that hole there and make it where these two values were both the same, whether they were both 3, 7 or 3, 8, it doesn't matter. If they were both the same on each piece, then it would make it continuous. All right? So that's how you fix these, is you've got to fix a hole. All right? So let's look at the next one, and this is exactly answering that question. So I have this piecewise function, and basically, see where this one breaks at 1. I can't graph this because there's a k, and it says, will you find the value for k which makes this continuous? So the whole idea is I've got to make basically this function and this function meet at the same point, and then I can do that. So here's the technique to this. So it breaks at 1, right? So we're looking for making our y's the same when I put those x's in so that it can continue. So if I take the left piece, or the top piece, 4x plus 5, if I put it equal to kx squared minus 2 so that those points will meet, and you say, well, I still don't know what to do because I have x's and a k. Well, when does this break happen? Well, it happens at 1. So I'm going to place a 1 here and a 1 here. Okay? So I have 4 times 1 plus 5 equals 1 times x squared minus, excuse me, that's wrong, k times x squared. I put the 1 in the k spot. K times 1 squared minus 2. So I have 4 plus 5, or 9, equals k minus 2. So if I add 2 to both sides, k has to be 11 for this to be a continuous function. Let's check and see when we do that. So if I did this, my function now is f of x equals, okay, the left piece or the top piece doesn't change. It's still 4x plus 5 when x is less than 1. That's an x. But now the right piece is going to be 11x squared minus 2 when x is greater than or equal to 2. Now let's check to see if this works. If I put a 1 in here, which it doesn't include it, but it goes up to 1, I would have 4 times 1 plus 5, or that equal to 9. So the 0.19 is where it goes up to, but it's not included in that graph because it's less than 1. If I put a 1 in here, I'd have 11 times 1 minus 2, which is 9. So this one actually includes the 0.19, so now it's going to work. This is going to go all the way up to there, but not include it, but then this is going to start in that hole, so we just made it continuous. This is kind of what I do for a check, to make sure, okay, that makes sense to me. Now this next page, there's not a lot of writing on it, but I wanted you to have it for your notes so that you can see certain functions here. So I have f of x equals x. That's the graph. If you'll know what f of 0 is 0, yes, there's no holes or jumps, so this is continuous. Now I'm starting out with these, so I have x squared over x. This is my graph. There's a hole at x equals 0. F of 0 does not exist, so no, this is not continuous because it has a hole at the origin. Okay, let's look at the next one. The graph of 1 over x looks like this. Oh no, f of 0 does not exist again because see, there's no, this is a vertical asymptote here, do you see it? So there, that is not continuous. Then I have x over x, which you think is 1, but it's got a hole at 0 because x can't be 0 in the denominator. It does not exist, so there's a hole at 0, 1. The absolute value of x, if you look at this one, okay, this is the v, and I can basically do it without picking up my pencil, drawing this. So f of 0 is 0, so yes, it's continuous. Now I've got a couple things here. This one is trig, so I've got sine x over x. And when I graph this, and it has to be in radians, this I do want to write down. You have to make sure that you graph this in radians or this does not work. So I'm going to write radians here because it's very important. Okay? Then this is what the graph looks like, and if you'll see at 0, it doesn't exist again. There's a hole, so it's not continuous. Here I have the absolute value of x over x. It gives me a piecewise function. It does not exist here at 0. So there's a hole and there's a jump at 0, so it's not continuous. If I graph 1 minus cosine x over x, again in radians, okay, you'll notice there's a hole at f of 0, so this is not continuous. Then I have the sine of 1 over x. And again, here, the f of 0 does not exist because you can have a 0 here, and this is what the graph looks like. It's oscillating very a lot right here, but there is a hole in there. You just can't see it. Okay, there is a hole at 0, 0. And the last page is just to give you a little introduction to the intermediate value theorem. Is continuity tells us that a continuous function cannot skip values. Okay, this concept gives rise to the intermediate value theorem. The intermediate value theorem. Suppose f is continuous on a closed interval. If k is any number between f of a and f of b, which are your y's, by the way, or your, okay, these are your y's of a and b, okay, then there is at least one number c on that interval ab such that f of c equals k. Here's I have other links, but I didn't put the link on here. So here I have this function here that looks continuous. So if I pick f of 2 equals 1, which is the point 2, 1, and the point 10, 3 are on the graph, all right? So you say f of 10 equals 3 and f of 2 equals 1. See how I put them on the graph? What this theorem says is that there's a value so that between 2 and 10, the function will pass through every y value between 1 and 3. In particular, when y is 2, we can see that there's a corresponding x value between 2 and 10. So they're just telling you that this is continuous ever in between at all values. And so I'm showing you this little picture. If I use the point 5,2, you would see that it is in between those two values. That's just a little introduction to the intermediate value theorem. We're going to practice this more in class, so I'll see you in class.